Hello, everybody, and welcome back. I hope you had a nice break. So it's week 9 of Math 4400, and today I just want to take a little bit of a pause, and we're halfway through the class, even a little bit more than halfway through the semester. So I want to take a pause and go over what we've done so far, and then talk a little bit about where we're going with the second half of the class. So I have a 3-year-old daughter, so I've been listening to a lot of Encanto lately. And so I want to, well, if you've seen Encanto, I want you to imagine yourself blooming flowers everywhere and thinking, now what else can I do? Except your flowers are congruences. And if you haven't seen Encanto, it's a great movie. Anyway, so here's what we did in the first 8 weeks of the class. Sort of, I've drawn some sort of mind map. So in purple, we have like the main objects and ideas that we talked about. So we spent a lot of time talking about congruences or modular arithmetic. We spent a lot of time talking about prime numbers and cryptography. We spent a lot of time talking about these more conceptual ideas of these algebraic structures of groups, rings, and fields. We talked a little bit about polynomials, and we talked a little bit about quadratic numbers. And then in blue, I've sort of written down some of the ideas. It's like some of the main results that we discussed in each of those areas. So, I mean, by far the dominant thing in the whole class is the Euclidean algorithm. That's the thing that, especially in this first 8 weeks, just kept on coming up over and over again. The Euclidean algorithm was at the basis of how we did all of our computations with congruences. I mean, we used the Euclidean algorithm to show that there's unique factorization. We use the Euclidean algorithm to show, to prove the Chinese remainder theorem. We use the Euclidean algorithm to compute inverses. And somehow computing inverses played a huge role in cryptography and all over the place. So somehow the Euclidean algorithm was really central to what we did in the first 8 weeks. But then all of these other ideas were really important. So we started out doing the Euclidean algorithm so we could prove unique factorization. And then we sort of moved into congruences. We talked about continued fractions a little bit and their relation to the Euclidean algorithm. And then sort of later on, we came back to continued fractions. Just briefly on the quadratic numbers worksheet, if you did some of the optional things, but we're going to come back to that connection a lot more. In the very first continued fractions worksheet, you saw that continued fractions were somehow connected to, were interesting for square roots. And we're going to hit that idea again in the second half. We'll sort of use all of this group theory and ring theory stuff more seriously, like the Grange's theorem and looking at finite fields. So this all will come back. We're going to do a little bit more cryptography. So we'll do sort of a more advanced cryptography scheme. And we'll study sort of a little bit more about prime numbers and unique factorization and what that means in sort of more general settings of groups, rings, and fields. So all these ideas that we encountered in the first 8 weeks that are written up here, we're going to come back to all of these. So somehow what you should think is that you now have the building blocks, like the main conceptual framework, the main conceptual ideas you need for the rest of the class. And now we're going to sort of see how we can connect these in more interesting ways and sort of see how we can solve really interesting problems using these ideas we've been developing. So that again, the second half class is less about sort of coming up with new tools and more about sort of seeing how the tools we've already learned can be used in more refined ways, and can be really, if we understand them a little bit better, how we can use them to really make some interesting observations and treat some interesting problems. Okay, so that's where we're going. So we're going to really talk about 4 things in this remaining 7 weeks. So the first thing, which is going to take probably the next 2 or 3 weeks, and we're going to start on Tuesday, is we're going to talk about squares modulo p. And then the big result in that area is something called quadratic reciprocity, which we'll see more about on Thursday. But this is a really interesting subject that sort of really hits these bottom areas a little bit more. So it's related to quadratic numbers. I mean, somehow squares are related to quadratic numbers. It's really intimately related to finite fields and sort of things we did with constructing finite fields using polynomials. yeah, so sort of hits sort of this area a little bit more. The next topic we're going to talk about is sums of two squares. And so that's going to be, so this is sort of looking at like when is a squared, when can you write a number n as a squared plus b squared? So this is something we actually saw in the very first worksheet. This was one of the exploratory problems that we did. And we're going to come back and sort of use the theory of quadratic numbers to answer that question. Sort of when can you write a number n as a sum of two squares? But that sort of connects also pretty tightly to the theory of unique factorization. So that sort of is going to hit this realm, quadratic numbers, unique factorization, primes, and so on. So we'll answer an interesting question, like just sort of when can you write numbers as a sum of two squares? But in doing so, we're also going to shed some light on sort of this like essential theoretical idea about numbers of unique factorization. Okay, so that's sort of the second thing. And the third thing is Pell's equations. So these are solving equations of the form x squared minus dy squared is equal to 1. So x, y, and d are integers. And usually we should take d to be square free. So this is somehow like a fairly innocent question. If I write down, so say I take a d to be 2, and I look like x squared minus 2y squared is equal to 1, I can ask, like, can I solve that equation using x and y integers? And so if so, like, how many ways are there to solve the equation? But this ends up having some really interesting structure to it. And actually, like, and you see lots of interesting things here when you try and solve this equation. So we'll come back to sort of, we'll hit this, and this sort of really touches on a lot of the stuff down here of quadratic numbers. It's sort of closely related to stuff we did with continued fractions earlier on. And again, sort of it's tied up with unique factorization in a really interesting way. So we'll talk about that as our third topic. And then the final topic, probably in about the last week of class, is going to be something called elliptic curve cryptography. So this last topic, it won't be on the final exam. And so we'll sort of do it a little less thoroughly than the other things and just try and give a picture of it, the main ideas. But this will sort of take some of the things we learned when we're talking about Pell's equation. So sort of, I mean, somehow it will be useful to think about Pell's equation geometrically sometimes as well, and related things. And so, and this sort of takes that to, this will take that to next step and sort of somehow combine sort of the study of numbers and the study of geometry to give you sort of some interesting new hard problem that you can use to do cryptography. So if you remember from when we talked about RSA and Diffie-Hellman, this sort of main thing in cryptography is you needed some problem that was like easy to do one way, but hard to do it the other way. So it's like easy to multiply prime numbers. It's hard to factorize a prime number. Or it's sort of easy to raise something to an exponent, like using the repeated squaring method, for example, like to raise something to an exponent mod p, but it's hard to take a discrete logarithm mod p. So that was sort of the main thing in cryptography. And so the theory of elliptic curve cryptography will sort of introduce a new setting, the theory of elliptic curves, that's sort of based in geometry and arithmetic, that gives you a sort of another hard problem to solve that you can use to do cryptography. So this is an important cryptography scheme. And that sort of really connects sort of this cryptography area down, sort of in some sense, all the way down to the quadratic numbers areas, but also sort of, it really sort of relates cryptography and sort of the theory of groups and Lagrange's theorem and all this stuff we were using cryptography before, but sort of in a more advanced way. And sort of, well, it sort of hits polynomials too, so it sort of hits this sort of part of things. Okay, now primes are involved in everything, so maybe it hits all of this. And even congruences. Okay, so the elliptic curve cryptography sort of puts everything together for a nice, interesting, and real world application. Okay, so that's where we're going with the rest of the class. And good, so I'm looking forward to it. And on Tuesday, we're gonna get started by sort of some preliminary investigations into squares modulo p, building up to this first thing. So this first thing is gonna take 2 to 3 weeks. Then each of these will take maybe around 1 week or a little more. And then this last thing will be about a week. Okay, I will see you in class on Tuesday. Thanks, everybody.